Welcome back to another video. Today we're going to be doing one of the hardest problems that I've ever done on this channel. We're going to be deriving the gamma function. And if you don't know already, this is a function that extends the factorial to even negative numbers, fractional numbers, and so much more. Brief recap if you weren't here for my last video. The factorial, in our simple terms, we define the factorial as multiplying the numbers or integers that are consecutive that go down to 1 with an increment of -1. This is the simple definition that we all know. Since this is going to be a long video, I'll be kind of skimming through all the very basics, so I recommend watching some other videos, or you can leave a comment down below if you don't know like the basics of calculus or more you want me to do videos on that. So the small recap which I'll do, which is essential of course, is as I stated earlier, the factorial function, as we typically define it, we think of it as being recursive. So we can think of the factorial function for, this only applies to some numbers, not all numbers, of course, there are infinitely many, but n factorial is equal to n times n minus 1 factorial. So it's recursive. It's the current number times the current number minus 1 factorial. This is about all you have to know about the factorial function to get started on this. So with that, let's begin. The gamma function is honestly a beast, but we're going to be seeing how and why it is an extension of the factorial function. The way I'm going to be doing this is I'm going to be starting off with a term called x to the n. I have some number x and some number n, where x is our input and n is a given arbitrary value. Let's say we differentiate x to the n with respect to x. Let's see what happens. And by the way, I'll put my definition. N factorial equals n times. This is the basic definition of the factorial function that we said earlier. But yeah, this is the basic definition, not the full definition, which we're going to be doing today. So ddx of x to the n, this is equal to nx to the n minus 1, as you recall from power rule. Now, what happens if we take the second derivative now? The d squared dx squared of x to the n is equal to the derivative of this, since this is the first derivative. What's the derivative of this? Well, this is just a constant, and we have x here, and then we have something else in the exponent. So we can use power rule again. We have n, which is our constant, we bring it down, and then we bring down our exponent using power rule, times n minus 1 times x, and then we have to subtract 1 from the exponent because of power rule, n minus 2. So you'll begin to catch on a pattern, but we'll do it one more time so you can see. Now the third derivative of x to the n is equal to the derivative of the second derivative of this. Same thing, this is constant, x, and then constant. A constant in the exponent. So we can use power rule once again. Now we have n times n minus 1 times n minus 2, because we brought this down, times x to the n minus 3. So we can generalize this a step further. Now the nth derivative, dn of dx to the nth of x to the nth, is equal to n times n minus 1 times n minus 2 ... of x to the, we're using the same variables, but generally we're saying this is equal to n factorial times x to the n minus n. We used n right here as an arbitrary value, but we can say that this is the mth derivative for simplicity, so n minus m. Simple like this. So with this definition in mind, we can see how just by using x to the n, we immediately get something involving the factorial, because we constantly multiply. When we take the derivative, we keep multiplying by numbers one less and one less and one less until we get something like this. So we've got the basic part of the problem done now. Let's move on into the harder part now. So the second part of the gamma function, if you don't know already, has to do with E, which is Euler's number. And I want to do a separate video on that later when I have time. But let's first take this expression right here. This is the second expression we're going to be dealing with. The integral from 0 to infinity of e to the negative a t dt. How do we evaluate this? Now, let's see. We're integrating with respect to t, so what we can do, it's very simple. A here is just a constant, so it's an arbitrary value. We don't have to worry about that. And if you evaluate this integral, it will just be, using our basic rules of integration, we get negative 1 over a times e to the negative at evaluated from 0 to infinity. U is equal to negative at. Du is equal to negative a dt. Then we have du over negative a is equal to dt. So you can substitute this back in. Therefore, we have the integral from 0 to infinity. Now we can plug in this negative a because we're trying to replace dt. dt can be replaced with du over negative a. So we get negative 1 over a, which is just a constant. So we can pull this out. Negative 1 over a. And then we have e to the u du. If I ignore the bounds for now and I get my indefinite integral, I would have negative 1 over a e to the u plus c, and then negative 1 over a e to the, what is u? We have negative at, just like this, plus c. And since we're evaluating definite, we ignore the c, so we drop this, and voila, we have what we had right here. But I kind of skipped that step. If you can do that in your head, that's great. But yeah, if that helps, let me know. So right here we have the integral from 0 to infinity of e to the negative at dt is equal to negative 1 over a e to the negative at, all evaluated from 0 to infinity. So it's actually evaluated now. And let's see what happens. It turns out, to evaluate this integral, we can simply use limit, since we're using infinity up here. So this is all equal to the limit as, and remember, we're doing this with respect to t. So we have as t approaches infinity, and we can pull the constant out, negative 1 over a, e to the negative at, all minus, since this is an integral, the fundamental theorem of calculus. We have 0 right here, so we just plug in 0 for t, minus negative 1 over a e to the 0. Beautiful, just like that, okay? So once we do this, what do we get? As t grows and grows and grows, e to the negative infinity, what is this equal to? This is equal to 1 over e to the infinity. This is not mathematical. This is like scratch work to help you visualize what's happening here. As t grows larger and larger and larger, this term e to the negative at becomes closer and closer to 0. It approaches 0 infinitely, or I mean, it gets infinitesimally close to 0. That's what I mean. So as t grows, this entire term becomes 0, which is pretty cool, honestly. So we have 0 right here, and then this minus becomes a plus. So we have 0 plus 1 over a, and what is e to the 0? E to the 0 is just 1. So, ladies and gentlemen, this integral from 0 to infinity of e to the negative at dt is equal to just 1 over a. Quite beautiful, isn't it? So, now here's the funny part of this entire trick that we're using. Let me simplify everything down. The gamma function arises when we incorporate both of these terms into a single form. And you're about to witness that in a second. But let me quickly move this over. So we can say that this is all equal to 1 over a. Oops. 1 over a, or a to the negative 1, whatever you want to say. So if I rewrite this in more simple terms, the integral from 0 to infinity of e to the negative at dt is equal to a to the negative 1. And there's a reason I wrote it like this. Now, on both sides, take the derivative. Take the nth derivative with respect to a, because on the right side we have a. We don't have a t. So if I take dn, dA to the n on both sides, dn, dA to the n. So the nth derivative with respect to a on both sides, we're going to be noticing a very interesting pattern here. So what happens on the right side first? We're going to start with the right side because it becomes a lot easier to do the right side first. But yeah, so in simple terms, I'm going to be saying integral from 0 to infinity. So dn, dA to the n. of e to the negative at dt is equal to, well, what happens when I take the first derivative of this? The first derivative of a to the negative 1 is equal to negative a to the negative 2. Now, what if I take the second derivative? Then what would I get? I would get negative 1 all times negative 2 times a to the negative 3. You see where it's going? Now, if I take the third derivative, I would get negative 1 times negative 2 times negative 3 times a to the negative 4. Now, you'll notice a pattern emerging here. We can generalize this a step further. You notice that we have, if we ignore all the negatives on the right-hand side here, we'll notice something very interesting. We have 1 times 2 times a to the negative 3. 1 times 2 times 3 times a to the negative 4. It's almost like a factorial is emerging from this. So once again, we said this was the first derivative, this is the second derivative, and this is the third derivative, and this pattern continues. So it's almost like we can say, we can pull out this negative sign because it's alternating. When this entire thing becomes negative, if we simplify this down, this is negative 3 factorial a to the negative 4. Simple. And right here, this is equal to positive 2 factorial a to the negative 3. So what does this mean? So we can say, oops, let me move this over. This gets a little confusing, so let me know if you need something to be clarified. We can say that this is just negative 1 to the n, because when I take the first derivative, I get a negative, right? So if I take the first derivative, this n will equal 1, and this will be negative. And then it alternates from there. This will equal negative 1, and then n factorial right here. So we have negative 1 to the n, which is alternating, n factorial, and then we're left with a to the negative n minus 1. Now let's confirm that we actually did this right. When I take the first derivative, let's plug it in. When I take the first derivative, n would equal 1. I'll do this in blue so it's clear. N would equal 1, so I do have a negative. Then I would plug in 1 for n here as well, 1 factorial. That's equal 1 times, and then I have a to the negative n. What is my n? 1 here. Negative 1 minus 1 equals negative a to the negative 2, which is indeed our first derivative. Let's try for the second derivative. Then we get negative 1 squared, which is what this formula is telling us, times 2 factorial, and then times a to the negative 2 minus 1, because it's 1 less. This is always 1 less than the order of the derivative that I'm taking. And now if you notice, we have 1 times 2 factorial times a to the negative 3, which simplifies down to 2a to the negative 3. Absolutely beautiful. And if you simplify this down, yep, that's exactly what our second derivative is. So yes, this formula does work, and it makes sense too. Negative alternates, we get the n factorial pattern, and then we just take a to the negative derivative we're taking, subtract 1 because of power rule. So now that we have this, we can continue and now do the left-hand side. So I'll leave this here if you want this. Oh, yeah, okay, that works. Now for the left-hand side. Very simple, actually, but it looks a little daunting at first. If we bring this derivative in, that is valid, mathematically speaking. So let's do that. The integral from 0 to infinity of dn dA to the n, or the nth derivative with respect to a, of e to the negative at dt is equal to negative 1 to the n times n factorial times a to the negative n minus 1. It's a really hefty equation, but we made a lot of progress. So once we're here, how do we differentiate this now? Well, let's do the same thing we did last time with the different order of derivatives. Let's take the first derivative. So let n equal 1 in this case. So that becomes really easy. What is dda of e to the negative at? Simple. That's right. We get negative t e to the negative at. Just like that. Whatever is up here that's not a just comes down here. That's all. So what if we take the second derivative? D squared dA squared of e to the negative at. This will equal the derivative of this now. And remember, since we're differentiating with respect to a, we treat t like a constant. So this becomes negative t and then times oh wow, negative t, because all we did, this is like we treat this as an outlier, or an outsider, I mean, and then we differentiate this, and to differentiate this is just this. So we get negative t e to the negative at. Once again, once we do this again, we get d squared, d cubed, dA cubed e to the negative at is equal to negative t e to the negative at, and this is just equal to negative t cubed e to the negative at, and up here we got positive t squared e to the negative at. So folks, we just used this pattern earlier. We saw that we had negative, 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 and it's alternating based on the order of the derivative we're taking. When we took the first derivative, this was negative. When we took the second derivative, it was positive. When we took the third derivative, it was negative. So once again, we have the case. We can say that, we can generalize this further by saying dn, dan, or the nth derivative with respect to a of e to the negative at is indeed equal to negative 1 to the n, because this is an alternating negative 1 series, and it starts on the negative. So when n is equal to 1, when you're taking the first derivative, this will be negative. So we have negative 1 to the n once again, times, and what's the pattern here? We have t squared here when we're taking the second derivative. We have t to the 1 here when we're taking the first derivative, and t cubed when we're taking the third derivative. So the order is just equal to, or the power of t is just equal to the derivative we're taking. So negative 1 to the n of t to the n, and that, so yeah, we get, and then e to the negative at, just like that. So we have the nth derivative of e to the negative at with respect to a is equal to negative 1 to the n, which is alternating negatives, times t to the n, which is just t raised to the power of the derivative we're taking, once again times e to the negative at. Phew, okay. Let's plug all of this in so we can finally see what we're working with. Now, we were substituting this back into our integral. Now we get I'll write this in white for more generalization. Okay. The integral from 0 to infinity of this inside, which we calculated through this massive process, we said was just equal to what? What is this? What is the inside of, what is this entire thing equal to? We said that this was equal to this. Since the integral is taking respect to t is not a constant within the integral, so we can't just pull it out. And since there's a t here, we can't just pull it out from here either. Now, negative 1 to the n is just a constant, so we can pull this out right here. Negative 1 to the n, just like that, with n being the nth derivative. And then we have t to the n, or n being just some independent value, I mean. Now, negative 1 to the n times times the integral from 0 to infinity of t to the n, e to the negative at dt is equal to what on the right-hand side? We have the same thing right here. So I will highlight this, and I'll just copy and paste. So you can see what we did here. This was what our right-hand side was equal to. So watch this now. This is going to be very cool. Well, we said n was an arbitrary number, and that's fine. That's like our independent variable. But what is a? A is another arbitrary value, making this function kind of multivariate. It makes it a function of two different numbers, introducing like a third axis maybe. It gets confusing. So check this out. We said that a can be any arbitrary value, making it its own independent variable. But what if we just let a equal 1 for simplicity? So let a equal 1. This is how noted mathematically. From this, we can conclude that if we do let a equal 1, what happens? This goes away, and this entire term goes away, because 1 to the power of anything is equal to just 1. So this entire term goes away, and it's really nice and simple. Now check this out. This is the climax, folks. We have negative 1 to the n here, the alternating negatives here, and negative 1 to the n here as well. We can divide on both sides, and that cancels because they're both the same n. They will always be the same. So we can cancel this, cancel this. Simplify terms. The integral from 0 to infinity of t to the n, e to the negative t, that's an interesting t, e to the negative t dt is equal to n factorial. That is all we're left with right here. And ladies and gentlemen, this is our definition of the factorial, the extended definition. So the gamma function of n is equal to the integral from 0 to infinity of t to the n minus 1 times e to the negative t dt. And this is all equal to n minus 1 factorial. And this was due to technical reasons and for more later advanced mathematics. They liked it being shifted off by 1, and it made it for more easier calculations. So what they did is they just said the gamma function of n, gamma of n, is just equal to n minus 1 factorial. So alternatively, if you want n factorial, this would just be gamma of n plus 1, which is equal to integral from 0 to infinity of t to the n e to the negative t dt, just like that. And that would be n factorial. Now, it is good to note, and by the way, if you do see this in other definitions, you'll likely see n be z, just convention, and honestly, to me, it looks cooler. I like z more, but yeah. Good to know, though, that n or z, whatever you want to call it, it should exist in the real world, at least. That would be ideal. Some people like to say the natural numbers, but yeah, as long as this isn't the reals, you're in the good zone. There are more advanced formulas, though, for complex numbers and plugging them into the factorials. And I can do a separate video on that, but there's entire graphical representations of that and crazy things you can do. But ladies and gentlemen, to answer your question, the gamma function, gamma of z, is equal to the integral from 0 to infinity of t to the z minus 1 e to the negative t dt. And you can see where this comes from, and this is all equal to z minus 1 factorial. And you can, as you've seen today, you can see where all of this comes from and how the factorial series emerges just in everyday mathematics, even in our power rule too. And we can combine properties of e and the fact that it's the derivative of e to the x is e to the x itself, and likewise the integral as well. And you can get a really nice looking term for what the factorial is. And when you graph out the factorial function, it looks absolutely remarkable. I'll post a graph right here. Folks, you can see the x factorial graph right here, and this is only possible due to the gamma function. As you can see right here, this is our standard gamma function going up and up and up like this, and you'll notice there's a minima here, which is really cool. I find that interesting. And you'll notice at the negative integers, x equals negative 1, there's an asymptote here that the graph approaches on both sides, and this occurs at x equals negative 2 as well, and x equals negative 3. It happens at all of these different integer values in the negative world, which is I find really interesting. And you can try and plug it into the gamma function yourself. But yeah, the gamma function is super useful in the real world. It's used for computations, even in computers sometimes, but rarely. No, not. It depends on what field you're going into. Yeah. If you have any questions, let me know down below. And as a bonus problem to all of you, if you've stuck this far, I want you to algorithmically find the solutions to x factorial equals pi. Give me all of the solutions and algorithmically post an answer. And if you do it correctly, I'll pin your comment. Thank you guys so much for watching. I really appreciate it. Leave your comments down below. Any questions, don't hesitate to ask. Thank you guys. Drop a follow. See ya.